Do you guys know what I'm talking about? Okay. Probably was supposed to give you something. Graphs, yeah. So, I like to study things that I call statistical connectomics. Connectomics. I'll give you guys a review paper on it as soon as I write one, but it's too new, so I haven't written that yet. But the basic idea is to think about brains as networks and to think about the statistics of them. So, raise your hand if you have a brain. Excellent. That's pretty cool, right? I mean, it's hard to think of another thing that everyone here would have, for sure. What? Heart. Some people might not have hearts in here, right? I mean, you guys are a little young to be walking around with fake hearts. I guess they have those that you can walk around with. But yeah, hearts are a good thing to have, but they can be replaced. What else might be hard to replace? Yeah? Liver. Yeah, it's another one. Do we have fake livers yet? No. I was watching Sherlock the other night. In Sherlock, they had this company. It's a TV show, but they had a company where they could build synthetic livers by 3D bioprinting. I don't think that exists yet, but it's not that crazy for a liver. They're kind of simple. And you can live without most of a liver. I think people do live without livers, right? No, they die?
Yeah.
How long can you live without a liver?
A day.
A day? It's pretty long. How long can you live without a brain? I'm not sure any amount of time, right? If you take it out, you're kind of not really you anymore. You take out your liver, it's like annoying for a while and then you die. So anyway, brains are important. Who here has heard of artificial intelligence? Nice. You guys know Marvin Minsky? He's one of the founders of it. He thought of himself to a large degree as a neuroscientist. Another person who did a bunch of cool stuff. You ever hear of a Palm Pilot? I don't know. That was probably made before you guys were born, right? When did Palm Pilots come out? 1990? When were you guys born? So yeah, it was before you were born, maybe. Well, anyway, that dude, he thinks of himself as a neuroscientist too. Lots of people who study intelligent systems, artificial intelligence, technology, they all are secretly neuroscientists or want to be. And a lot of them, including me, think about the brain in a variety of ways, but one nice abstraction of the brain is a network. So those of you who have taken a class before in something related, you know what networks are, but just to be a little bit pedantic, this is an engineering class. In math world, we say this thing is called a graph, and it's a tuple. There's two things in here. This is a vertex set. People also call them nodes and other stuff like that. And this is an edge set. And people call these things edges or lengths or sometimes arcs. And so if you had a graph with a few nodes, say here's some nodes, and there's some edges, that's a graph. There's nodes and edges. The nodes don't necessarily have names, they don't have locations. So I could rewrite this graph in a variety of ways. So I could move, say, this node and this edge and put it over here. That's the exact same graph. The graph is this abstract mathematical thing where there's vertices and edges and there's nothing else that exists. Right? It's a set or a set of sets. That's a graph. Now, as it turns out, people decided around 1900 that brains might be networks. So does anyone know what people thought brains were before 1900? Heat sinks, partially that, yes. Also, they thought a brain was a syncytium. So you should look that word up and have fun doing that because it's really hard to spell. Try a whole bunch of things. Eventually you'll get it, syncytium. There's S's and Y's. And so a syncytium was one big cell, basically, with a whole bunch of different nuclei. And around 1900, people started coming out with better microscopes, and they determined that brains aren't syncytii, but rather they're cells. And like here's maybe a cell body, and there's some axons and dendrites, and these are processes. And then here's another one over here. And then maybe this guy forms a synapse with that guy, and they're connected. So that's a synapse. You guys all know what synapses are. This is a soma in the cell body. This relatively familiar. Okay, so when people started being able to see this stuff, which is small, like on the order of cubic microns, they thought, hey, brains are networks. There's a whole bunch of things, nodes or vertices, and they're connected to each other by synapses, which are the edges. And therefore, we should study them as networks. And that was a great idea, except for it didn't really have the tools, so you had to wait about 100 years. And they all died. But then we were born. And now we really can study brains as networks, because there's lots of tools that let us take lots and lots of images of brains and try to estimate the networks. And these guys over here do that all the day. You can talk to them about that later if they don't leave before. So, okay, brains are networks, and that's great. But you guys have all taken probability and statistics. So you know some stuff about random variables. So let's talk about random variables for a minute. Someone name a random variable. Come on. What? Say it louder and less mumbly. X? X is a random variable? Great. What's the distribution of X? There's no, well, I guess there's some wrong answers, but there's many right answers. So you have a good chance of being right if you say something.
Uniform.
Uniform. Uniform between 0 and 1?
Sure.
Okay, great. This is a wonderful random variable. Okay, and so we could write X takes samples, live in, we write like this, 0, 1. So X is a random variable, and samples from this random variable, or we write little x, and they live between 0 and 1. Okay? That's a great random variable. It happens to live between 0 and 1. Let's name another random variable that comes from a different distribution. So X, what's another distribution? Gaussian, that's a good one. Let's say it's standard normal Gaussian. So now, samples from X, where do they live? Would they have to be between 0 and 1? Negative infinity to infinity. Also known as R, the real number line. Cool. Okay, those are good ones. What about, say, Bernoulli? You guys know Bernoulli? Okay, Bernoulli. There's a probability P of it being heads or tails. Okay. So little x, where does it live? Zero or 1. That's a good option. Another option would be, say, heads and tails. Or sometimes people like doing -1 and +1. Okay, so you guys are aware of this concept of random variables, and you're aware that samples from random variables can live in different spaces. And you're aware that there's networks. All right, so we're all on the same page here. The thing that I would like to spend the next however long we have until you guys leave is understanding that there's something called random graphs. Okay? These are random variables whose samples are graphs. And so just to be clear, it's not the edges that are random variables, it's not the vertices that are random variables, the graph is a random variable. But we're going to build that up from the basis of Bernoulli random variables. Bless you. So can anybody name any graph-valued random variables? There are many distributions on graphs, but I happen to know them. I'm betting no one here does, because why would you know that now until I tell you? So does anyone know of any? Okay, so do you know one? Erdos-Renyi? Yes, that's the best one. At least the simplest one, which is where I always like to start. So let's say X is a Erdos-Renyi random graph. So Erdos and Renyi were a couple badasses in the 50s who basically developed graph theory. And they also did a bunch of more stuff. You can read about them. They're awesome. So does anyone know what an Erdős-Rényi random graph is? The person who knows it exists might know what it is, or might just know that it exists. He's now hiding behind his computer. That's fine. I know what it is, so I can tell you.
I think it's like almost like a. I got the name.
Follows what?
It's like, I guess, like given like n number of nodes, right? You can just like follow like random connection.
Yeah, that's basically right. I'm going to be a little bit more precise, and I'm going to say that if you have n vertices, let's say n happens to be 4, the probability between an edge for any pair of vertices is p. So the probability of an edge from here to here is p, 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 right? It's all p. Okay? So every edge is independent and identical. So every edge is a Bernoulli. Right? They're all independent and identical Bernoullis. And there's a whole bunch of them. So we can write down one. Let's say, here, this is one. And I'll just label these vertices for a little bit of clarity. And now I can write down what we call an adjacency matrix. A, B, C, D. A, B, C, D. And I will put a 1 down wherever there's a connection. So is there a connection from A to A? I didn't really specify whether that's even allowed, so that was a bit of a trick question. Let's come back to that. What about from A to B?
Yes.
A to C? A to D? B to C? B to D? C to D? Okay, these are all the ones. I'll just leave the bottom part off. Well, I'll put them in there. So, if there's a connection from A to B, what we've said kind of implicitly, there's no arrows here, right? It's not like it's just from A to B or just from B to A. So there's a connection both from A to B here and B to A. And that's because when there's no arrows here, and in an Erdős-Rényi random graph, it's called undirected. Also, I didn't say anything about whether you're allowed to be friends with yourself. So, anyone here on Facebook? Raise your hand if you're on Facebook. Really? Still? Isn't there something cooler yet? Really? That's definitely not the answer. Okay, so you guys presumably you're on Facebook. You have friends on Facebook. Can you be friends with yourself on Facebook? No. Yes? How did you do that?
Message yourself, right?
I don't know. I've never tried that. Why would you do that? You just say it out loud. You'll hear it. Okay. But you can't be. Can you friend yourself? No, I didn't think so. So Facebook, in Facebook there's a network. It's a pretty big network right now. I think there's about 1 billion vertices. Probably. Does anyone know? About 1 billion user accounts in Facebook and maybe 100 billion edges? But it's undirected, right? If I'm friends with you, you're friends with me. I haven't figured out, at least yet, how to not be friends with someone when they're friends with me. And you can't be friends with yourself. So if Facebook is undirected, it's also, it's called, there's no loops. So a loop would be a connection from yourself to yourself. You can't have that in Facebook. And you can't have that in a simple graph, which is what we're writing down. Also, you note that all of these connections, it's just whether it's there or not, right? There's no weights. You can't be more friends with someone. Or in Facebook, can you be like better friends with someone? You can? How do you do all this stuff?
You can follow them and you can see their posts first, and you can also get notifications from their status.
Wow, Facebook's super complicated. Okay, well, I'm just going to say that that's not possible because it's ruining my thing. So I'm going to say the graph is binary also, meaning there's edges or there's not. There's no way to have like multiple connections between any pair of people. If you have all that, you are a simple graph. It's just vertices and edges. There's no directions, there's no weights, there's no loops. And ergo Shreni is the simplest way of sampling a random simple graph, right? You just look for each pair of vertices that aren't the same. You say, with probability P, you put an edge here. With probability P, you put an edge here. Probability P, you put an edge here. And you go through the whole thing. Okay? That's the simplest random graph. Now, you may say, well, who cares if there's random graphs? And so I will say, well, science cares and medicine cares. So anyone here has ever read like a paper about medicine? Like if you eat meat, you get colon cancer? Something like that? So you may have noticed that in that paper, they have done some statistics. Right? They measured a whole bunch of things like how long you live and how much meat you have, and then they determined that if you eat a lot more meat, then you die a lot sooner, or whatever. Right? That's statistics. That's all of what statistics does. It lets you estimate population properties. Like the probability of dying soon if you eat meat is really high. Now, all of that 100 years of statistics since Fisher started doing all sorts of good stuff with P's, all the way until now, has focused almost entirely in this domain. Random variables were binary, or they lived on, say, 0, 1, or they were in the real number line, but they did not live over here. So the random variables weren't graphs. The reason that's interesting is because if we say lots of people have brains, basically all of them, and some people have psychiatric disorders, or some people are like super geniuses, and we think that part of the reason that they have these disorders or they're super smart is because of their connectivity, and we want to know how much we should believe that, that's a statistics question. And it's a question about the statistics of the networks. Okay? So this is why we care. If we believe that networks are a good representation of any kind of data, for my case it's brains, but maybe Facebook or Twitter or whatever, if we have statistical questions about it, then we need to understand the statistics of the network and statistics of networks in general. So does that make sense? Do you guys believe that? So let's take a very simple example. Let's say we measured xi and yi for I in n. So what I mean is, say this is the brain network of person I, and this is whether, let's say, they've been diagnosed with bipolar disorder, just for fun. Because we could have chosen anything. And let's say I is in n, and we're going to just say, we'll make n 100. Okay? Network? Sorry. I'll write graph. Maybe I write that better, maybe. Okay, so we've measured for 100 people via some magic, which we won't get into for this class. We estimated their graph, and we know whether each one of them is bipolar or not, according to some psychiatrist. We don't know whether that psychiatrist was right, and we don't know whether our graph estimation was right, and we're going to ignore that for now and just assume they're both right. Okay, and so now the question is there something in here about their graph that tells us whether they have bipolar disorder or not? Right? Wouldn't it be cool if, like, let's say you got sick and you went to the doctor and they could say take your blood and tell you, oh, you have a cold or a virus. Has anyone ever gone and gotten a check to see if they have something bad? Like, I had to go check for rabies one time because I thought a bat bit me. But just as an example. But you guys have probably all been to doctors and they've given you a test and you say, oh, you don't have this thing or you do have this thing. Right? So in psychiatry, there aren't any tests like that. Right? You go in and you tell the doctor, I feel sad or happy more than I think I should. And they ask you a whole bunch of questions, and then based on that, they give you a whole bunch of drugs often. And those drugs are sometimes great and sometimes catastrophic. Because if they diagnose you with the wrong thing, you may end up doing something terrible. So you really want to be careful about these diagnoses. And there's literally no clinically useful biomarker based on imaging of people's brains for psychiatry. So you can't, if you think something is wrong psychiatrically with you and you go to the doctor, there's no tests. There's just questions. There's nothing they can do by measuring any biological property of you, genetics or imaging or anything else, to help them make a diagnosis, and more importantly, to help them give you a treatment plan that's helpful. But there's a belief that some of these things are related to the connectivity of your brain. And so, if we could determine which properties of people's brains were important in determining how they would respond to various treatments, then maybe we could have better treatment plans and better diagnostic tools and stuff like that. So, okay. Now, I'm going to say we have these 100 people, we measured their graph, and we know whether or not they're bipolar. So, what should we do? Right? You guys are the doctors, you got this data. You want to figure out, are the brain networks for people that have bipolar, are they different than the brain networks for people that don't? What might you do? Statistics, that's a great idea. Anything more specific? Yeah?
You can see if all of the people with bipolar disorder have some connections that the other people don't.
That's a great idea. So, I'll erase this. So I think you said, and correct me if I'm wrong, do a hypothesis test. And the null hypothesis is essentially that I'm going to write something else. I'm going to say xy is jointly distributed fxy. Okay, so there's a joint distribution of the brain networks and whether they have bipolar. And we know from the laws of total probability that we can write that do you guys remember that? You can partition a joint distribution into a product of a conditional and a prior. And you can also rewrite it like this. If you don't remember that, then look up Venn diagrams and you can convince yourself of this pretty immediately. Okay, so I think what you're saying, if I'm correct, is that one thing you can do is check whether f of x given y equals 0 is equal to f of x given y equals 1. And the null is that they're not equal. Is that right? Pretty sure it's what you meant. Great. Right, so she was proposing, sorry, tell me your name?
Alexis.
Alexis is proposing, we'll do a hypothesis test. The networks from the people that don't have bipolar are distributed the same way as they do. And the alternative is that they're not. Right? And so if we reject this, then we believe that there's a difference, and that tells us, oh, we can probably develop a test maybe, because those networks are different. Okay, so that's cool. But now we're doing statistics on networks. Right? So we need to write down distributions of a network. Does anyone know any? I'll give you a hint. Wrote it down earlier and then erased it. Erdős Srény? Great. Okay. So let's say we're going to say f of x given y equals 0 is Erdős Srény. So f of x given y equals 0 is Erdős Srény. What's the parameter? It's going to be p0. There's some distribution, some probability of there being an edge. This is literally the simplest possible statistic thing I can think of for random graphs. And now we're going to say f of x given y equals 1 is also Erdős Srény, but it has a different probability. Okay? What this means is basically what we're saying is maybe those people who've been diagnosed with bipolar disorder have a less probability of having connections between any place, and those who have been diagnosed have a greater probability. Right. Is this a good model? I have no idea. No one knows because I don't think anyone's ever checked. Maybe someone checked. They probably did the math wrong though. But we can do it right because we now know about random variables and we know about Erdős-Rényi. And so, okay, so how are we going to test that? There's just, basically we're just testing whether P0 and P1 are different. That's all, that's the whole name of the game. Right, so how would you estimate P0? Count the number of edges in, say, one of the graphs, and then divide by the total possible number of edges. Okay, that's P0 for that one graph. Now there's 100 total graphs. Let's say 50 are in group 0 and the other 50 in group 1. You just want to do the same thing for all of them? Yeah, so I think the suggestion is, so you have this adjacency matrix, which is a 0, 1 for subject I. And we sum over all possible edges. No, that's not a good way of doing it. Sum over all possible edges, and that gives us the total number of edges. And then we divide by n squared. And that's P for subject I. That's what you're saying, right? Okay, but now we're going to get that for all possible I. So we're going to have P1, P2, all the way up to P100. These are hats, because these are estimates. Okay, so now we've estimated the probability of an edge for each graph separately. Now what should we do? Let's say we know the first 50 all are y equals 0, and then the next 50 of y equals 1. What should we do now? Any ideas? How about we average all of these guys? Seems reasonable, right? I'm really just trying to think of the simplest possible thing to do. So I'm going to say our estimate of P0 equals the sum of all PI's where yi equals 0. And I can do the same thing for P1. Okay, now if they're really different, then we know they're really different. We just did statistics of networks, and we just discovered something new, that people with bipolar have more connections or less connections or whatever the answer was. You guys stoked? It's pretty easy, right? Yeah, you have a question?
Yeah, I'm wondering why we learn about Erdős-Rényi and all these other kind of distributions and statistical methods if we're just counting the number of connections.
It's a great question. So could everyone hear the question? Basically what he's saying is the first part of all the stuff I said was useless because we didn't need it. We just had to count, and we already knew how to count. And that's totally right. But in the next 15 minutes, we're going to write down slightly more elaborate random graph models where you're going to need some of that machinery a little bit more. Okay? Did I do your question justice? Yeah. Okay. So, you know, brains are pretty complicated, right? Humans have about 84 billion cells and about 1,000 trillion connections. And so, if we want to characterize them by some random variable with some distribution, an option is to characterize them as a random variable with one parameter, which is what we did. But maybe the differences between bipolar brains and non-bipolar brains is not just the probability of connections. Maybe it's something else, something more interesting and elaborate, like certain places in their brain are more likely to be connected or not. So why don't we write down a slightly more elaborate model that will give us more flexibility and more power to detect more subtle kinds of differences. So can you think of some more complicated way of sampling graphs. All right, the simplest way we already said. Every edge is identical and independent.
Edges have different importances.
What's that?
Edges have different importances.
Sure, that's a great idea. So I'm going to write that down and say, what we had before is there was an adjacency matrix. And each edge was identical and independent. And so what that means is there's a probability matrix. And this probability matrix, it's an n by n matrix. And the entries are all p. P, 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 P. They're all p. Right? And so what we're going to do for each element of this matrix, we just sample Bernoulli with probability p, 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 p. Okay. And the suggestion, sorry, what was your name?
Brant.
Brant? Oh, hi, Brant. Is to make these different, right? Make somehow some of these are more important or more interesting. So what if we say rather than they're all p, what if we say they're all just whatever they are? This guy is p11, this guy is p1n, this guy is pij, this guy is pn1. Every element of this m by n matrix is just a different number, right? So what does this mean? This means that, say, the probability of connection between, say, visual cortex and motor cortex might be p12, and the probability of connection between visual cortex and auditory cortex might be something else. So certain edges are more likely than other edges, which is true. In your brain, there's a pretty good chance that your, say, lateral geniculate nucleus is connected to primary visual cortex. Because anatomically, there's lots of evidence of that. But on the other hand, there's lots of regions that tend not to be connected. And this is done through histology and simulation and lots of experiments over the last 50 years. Lots of regions tend not to be connected, and lots of regions tend to be connected. And so this is a much more accurate model of how brain connections work. It's still way grossly oversimplified, right? Remember, there's 1,000 trillion connections, and we have n squared parameters. And n, I didn't specify, but the number, the number of vertices in this might be something like 100 because we partitioned the brain into 100 regions. Okay, so that's one slightly more elaborate model. And now we can get back to the suggestion of a different way of checking whether the two different classes of brains are independent, which is essentially do this exact same thing we did over here, but now we're going to modify it slightly to reflect the fact that the different probabilities for each potential edge. So how should we modify this procedure? Remember, we had this thing over here that gave us p hat I. This is the probability of an edge anywhere. What should we do? Yeah, the p's are matrices now. So we can kind of just more or less skip that part because that was the averaging over the edges. And this is the matrix. The probability of an edge for subject I between any pairs. Right? Now we don't actually have those probabilities. All we have is a matrix. We just have the adjacency matrix. So I'm not sure you totally followed what I just did, but we have this for each subject. We have a matrix. A1, A2, A100. And we just said, okay, what's the probability of a connection between I and J? Where I is, say, some vertex and J is the other one. Well, that's just the sum of A, I, J. The average number of people that had that connection. And since there's two groups, we would do that 2 different times. First condition on y is 0, and that gives us p0. And then we do it again for when y is 1, and that'll give us the answer for y1. Now we have these two estimators. And we can again apply this test, but now we can apply this test on each edge separately. Okay? And we've made a bunch of very simple assumptions. Every graph is independent, and all the edges are sampled independent. They're just sampled from a different probability. So, Brandt's question from before is still totally valid, right? You still didn't need any of this machinery. Fair enough. But let's say the dependence, the difference between these two classes was more complicated than just that. Let's say the difference between these two brains, these two populations of brains, were bipolar brains had more triangles, right? So here's a network. This is a triangle. I guess you guys knew what a triangle was. But that's a triangle. Maybe bipolar brains have more triangles than non-bipolar brains. Well, sure, if you knew that you were looking for more triangles, then again, all you do is you count triangles in bipolar brains, count triangles in non-bipolar brains, and say, oh, the bipolar ones have more triangles. But let's say you had no idea whether it was triangles or edges between one particular part of the brain and another, or maybe it's 4 cliques. This is another thing, right? There's 4 vertices, they're all connected to each other. Maybe it's 4 cliques. Maybe it's stars. Things like this, where there's a whole bunch of edges all onto one vertex, but none of those guys are connected to each other. Let's say you have no idea what you're looking for, but you know that you think there should be a difference. Well, you could try to enumerate all possible kinds of differences, and that might seem like a good idea. Like that. So, all these different things I was just drawing, triangles and 4 cliques and stars and edges, those are all properties of a graph. Okay, so let's say we have a graph and say there's 10 vertices or 20 vertices or 30 vertices. Just one graph, and this is n. Now, this is the number of properties that we can define. Now remember, it's finite because the graphs are simple, right? There's just binary things, and there's n vertices, so we can count all possible combinations of things. And so the plot looks like this. Okay, so now your question is, what is this value? When there's 30 vertices, how many different properties could you define? Take a guess. Who thinks more than or less than 8? Raise your hand if you think more than 8. Okay, keep your hands up if you think more than 800. 8,000. 800,000. 8 million. 800 million. You guys are all off by like 20,000 orders of magnitude. The answer is 10 to the 300 or so when a graph has 30 vertices. So obviously there's some intuition missing. So let me try to give it to you, and then we'll go play in the sun. Okay, so we have an adjacency matrix. Let's do the simplest possible adjacency matrix. There's 2 vertices. Let's allow for directedness and self-loops. How many possible adjacency matrices are there? Let's say even simpler. Let's say there's 1 vertex. How many possible adjacency matrices are there? 2. Okay, great. N equals 1. Let's do it like this. N is 1. Number of potential edges, or number of potential graphs. I'll do it like this. That G is a script G. That's a set of possible graphs. And this pipe here and here is cardinality. How many elements are in that set? That's 2. Okay. Now let's say there's 2 vertices. How many potential graphs are there? Let's just work it out. 1, 2, 3, 4. So it could just be one edge. So there's 4. It could be no edges. That's another one. It could be all edges. That's another one. What about pairs of edges? 1, 2, 3, 4. Is that right? Did I miss any? 10? 6? 8? What do you think? Did I skip anything? 3. Okay, great. What? How many ones of those are there? 4? So how many total? 16. That's cool. So let's try to get the intuition so we can extend, because you guys probably aren't going to count to 3, right? I mean, 2 was hard. 3 is going to be annoying. Okay, so this adjacency matrix has 4 elements, and each one can be binary. So let's just think about it for a second as a bit string. Okay? 1, 2, 3, 4. How many 4-bit strings are there? 16. How do you know that? Because it's 2 to the 2 to the 2? Right? This could be a 1 or a 2. This one could also be a 1 or sorry, this could be a 0 or 1. This one could be 0 or 1. Right? So 0, 1. And then 0, 0, 1, 0, 1, 1, 1, 1. Right, you guys know how to do binary stuff? Right, every time you add another element, it doubles the number of options. And since there's an option here for 2, if there's only one thing, there's 2. Times 2 is 4, times 2 is 8, times 2 is 16. So if there's 3, how many possible different graphs are there? What's the equation? 2 to the 3 squared? 2 to the 9? What's 2 to the 9? 512? Cool. What's 2 to the 30 squared? Which is this number over here. 2 to the 30 squared is what?
Actually says 2 to the 900.
Oh, 2 to the 900, that's right. Do you know how to convert from 2 to the 900 to 10 to the something? Well, I told you the answer. 10 to 300. You can do the math in your head if you want. Just take the log, and then anyway, you can work it out. So 2 to the 300 possible graphs. Each graph is a special case of a graph property of the dense graph. Right? They're just all different kinds of properties. They're all unique sets. So if there are 30 vertices, there's 10 to the 300 possible features that we could think may differ between these two populations of bipolar and non-bipolar people. Huh. So this is why we need statistics, because this simple model that we wrote down, it maybe went away. Yeah. Of every edge being independent and identical is super insufficient. And even to say that every edge is independent and not identical is still insufficient, because we're often looking for much more complicated kinds of differences between these networks. And we can't look for all 10 to the 300 possible differences. So what we can do is develop more elaborate computational statistical tools that will efficiently search not all 10 to 300 ones, but special cases of them based on having more elaborate models. And that's basically what I do all day long. 2:20 is when class is over? Class is over. Thanks.